Alright, and for our last video in section 14.5, we're going to look at question number 10 that says to compute the improper integral of the function x over the quantity x squared plus y squared plus z squared times e to the minus quantity x squared plus y squared plus z squared. And we're integrating over e, which is the first octant. And since this is an unbounded region, we have an improper integral. So let's go ahead and set this up as an iterated integral in spherical coordinates, and to do so we need to describe the first octant in spherical coordinates. So if you imagine fixing an angle phi and an angle theta, our radial distance rho will vary from 0 to infinity. Then for phi, that's going to have to vary from 0 when we're on the positive z-axis to pi over 2 when we're in the xy plane. And finally, theta will need to vary from 0 to pi over 2. Okay, so let's go ahead now and write down this integral. So x in spherical we derived was rho sine phi cos theta, and then we're dividing that by x squared plus y squared plus z squared, and that's just rho squared in spherical. Then we have e to the minus, well, that same quantity, x squared plus y squared plus z squared, so that's just rho squared. And now for our differential volume element, we're going to have rho squared sine phi, and then I'll go ahead and put in our bounds for rho, that's 0 to infinity, for phi here, that's 0 to pi over 2, and then finally for theta, that's from 0 to pi over 2 as well. Okay, so now notice that the rho squareds here and here can drop out. That's nice. And so what else are we going to get? We are going to get a sine squared phi, and then we also have the cosine theta, and then I'm going to group this rho with the e to the minus rho squared. So we're looking at this. Rho e to the minus rho squared. Then we have our sine squared phi, then our cos theta, and the order here is d rho, d phi, d theta. Alright, now our integrand is a product where the expression rho e to the minus rho squared depends only on rho, sine squared phi depends only on phi, and cos theta depends only on theta. And so now I'm going to go ahead and break that up as the integral from 0 to pi over 2 of cos theta d theta. Then we're going to have the integral from 0 to pi over 2 of sine squared phi d phi. And then lastly, the integral from 0 to infinity of rho e to the minus rho squared d rho. Okay, so this first integral, well, integral of cosine is just going to give us a sine. If I evaluate that at pi over 2, I get a 1. Evaluate it at 0, I get a 0, so I'm just going to get a 1 from that first integral. Now for the second integral, I have to do a little bit of work here because integrating sine squared is going to require a trig identity. So I'm going to use the fact that sine squared of phi is 1 minus cos 2 phi over 2. So here I'm going to integrate a half, and that's going to give me phi over 2. and then I'm going to integrate cos 2 phi over 2, so I'm going to get a minus sine 2 phi over 4. And we're evaluating from 0 to pi over 2, so we get that. And then for this last integral, since we have this rho hanging out front and we have a rho squared up in the exponent, that suggests making the substitution u is rho squared. And then we get 2 rho d rho for our differential. And so what are we going to get? Well, we'll get the integral of e to the minus rho squared, so that'd be e to the minus u. And then rho d rho is just du over 2. And then let's go ahead and change the bounds. So if rho is 0, u would be 0. And as we let rho approach infinity, then u would approach infinity. So we're looking at that. All right, so keep plugging away. For this middle factor here, plugging in pi over 2 is going to give us a pi over 2 over 2. So this is a pi over 4. And then here I'm going to get the sine of twice pi over 2. So that's the sine of pi, which is 0. Plugging 0 in, I'm going to get the sine of 0, which is also 0. So I really just get a pi over 4 from this middle factor. And so then that really just leaves the evaluation of this last integral. And that's minus e to the minus u, as we let u vary. Oh, sorry, don't want to forget the 1/2 there. So we got 1/2, and I'll put the minus in front. There we go. And now, as I take the limit here, as u approaches infinity, e to the minus u is going to approach 0. If I plug 0 in, I'm going to get minus 1/2, but that's being subtracted, so I'm going to get positive 1/2. So when all is said and done, this integral is equal to pi over 8. All right, pretty nice. And that's going to do it. Thanks.